In this part 2, we will understand the math behind the transformers, and we will understand how these transformers are capable of capturing the relationship between the words when a sentence is given to them. Okay, so I'm just revisiting the same slide as we saw in part 1. So the transformer is a foundation of large language models, and we all know, so the transformer is the core architecture on top of which the large language models is built. So yeah, so just to recall once again, so this is the architectural diagram of transformer that was published in the paper, that is Attention is All You Need by Google. And this is the encoder and this is the decoder. So at the end of this part 2 video, so you should be able to understand each of the components of this transformer architecture. Okay, so our goal is to understand how these transformers or the large language models are understanding the languages inherently. So that's what we are trying to understand here. Okay, so let's not forget the goal we are trying to build a LLM. So this we are talking about the pre-training. So we are understanding how these large language models are inherently built during the pre-training. So that's what we are bothered about here. And what is the core functionality of the transformer to make it, the large language model to make it a next sequence predictor. So how it is able to predict the next sequence. That is the goal, and we will understand step by step. Okay, so as of now, we will understand transformer as a black box wherein we give some input and we get some output. So in the part 1, we saw how we gave a prompt of writing a content, generating a content for LinkedIn post, and we also saw like how a code can be generated when a prompt is given. So we just see llama. We just saw llama as a black box. So we don't know like what's happening inside the black box. That's what we are trying to explore here. So here what I've given is the input sentence. This is Tamil sentence, Naan oru Manavan. So we are trying to translate this input sentence, Tamil sentence to an English sentence. But what happens inside the black box, we will see step by step. So inside this black box, we have encoder and decoder architectures, and these encoders are primarily when they are given with a natural language sentence or a paragraph or whatever, so they will convert them into a number representation. So we all know that these deep learning architectures cannot digest text. They can only digest numbers. They can only explore the numbers. So they can only process the numbers. So these encoders capture the relationship between each and every word given in the sentence deeply by understanding the grammar and the semantics of the words present in the sentence, and they convert into a richer representation. That's what these encoder do. Decoder job is also similar, but decoder's output is always in the form of a natural language a sentence. So here the input is a sentence, text, and the output is also a text. But what encoder gives to the decoder is the richer representation of the input. So that decoder can actually refer this in richer representation and do the translation task in an efficient way. So that's the way they function. So we'll understand what is inside the decoder. When we look deep inside the decoder, we have self-attention mechanism and the feed-forward mechanism. Self-attention mechanism we talked in the part 1. So it is nothing but like how the large language model is able to capture the relationship between the words. So we'll get to understand the self-attention mechanism and feed-forward mechanism deeply in the upcoming slides. So the decoder is also one and the same, but the only difference is that the decoder will have an reference from the encoder, so that it can refer the input representation and it can do the task of decoding. Yeah. So when you look at these large language models, they won't have a single encoder or a single decoder. They have a stack of encoders and stack of decoders. So certain large language models have 6 encoders and 6 decoders. So these numbers will vary depending upon the large language models. So that's what about what is inside the transformer. So step number one, like we have just understood that there will be an encoder and decoder, but not all the large language models will have both the encoders and decoders. So though the transformer architecture when published by Google had the encoder and decoder, these large language model, depending upon like for what task they are meant for, they will have the encoders and the decoders, or only encoder only models are also available, decoder only models are also available. So when you look at encoder, when you have a encoder only models, these encoder only models are mainly meant for predictive tasks. So let's say you wanted to understand the sentiment or movie reviews, or a movie sentiment classification, or tweet classification, or whatever. So these are the predictive tasks. So the output is not going to be in the natural language. So the output is going to be a class label, whether it is 0 or 1. So the 0 can represent any class, like positive or negative, whatever. So for those kind of tasks, the encoders are meant for. Whereas when you want to do a generative task like summarization, machine translation, code generation, content generation, like we saw in the part one, so those are decoders. So those architectures will have decoders. So large language models that released after 2021, that is after GPT 3.5, they are mostly decoder only based models. But we do have encoder and decoder together models like T5. So these models have both the encoder and decoder. So what I'm trying to convey here is that large language models will have either encoder or decoder, or both the encoders and decoders for depending upon for what task they are meant for. Okay, so now we will understand closer what's happening inside the encoder. Step number one, whenever we are given a sentence, so we are talking about like how these large language models are built during the pre-training phase, like how this GPT 3.5 was built during the, I mean, the when the OpenAI built those models, like that's what. So they would have during the training phase, they would have broken the sentence, each and every sentence given to them into token. A token you can think of like when a sentence like the cat sat on the mat is given, the is a token, cat is a token, sat is a token, and even you can see that like the full stop is also a token. In early days in natural language processing domain, so we used to throw the stop words like I mean these full stop hyphens we used to throw due to the unavailability of the computational resources. But current day in the current day large language models, so these large language models believe that like even a hyphen carries some semantic information, so they don't throw it away, so they consider that as a token. So you have very numerous tokenizers, word piece, byte pair encoding, so they tokenize word in their own way. So, but what primarily this tokenization mean is that like breaking the sentence into smaller units. A word can have more than one token. So, for instance, like if you take singing, so the singing will have two token like sing ing. So, depending upon the tokenizer that we are using, so we will have the tokens. So once the tokens are identified, they are given the unique ID. So that's what I said. Like the encoder is basically converting the text sentence to a number representation. So now this the is only given the number 101 and cat is given 1123. So that's how you can understand this. So we add special tokens. Initially these are the numbers representing just the words the cat sat, but they have not still captured the semantic deep meaning of the sentence. Slowly they will do so, but yeah, so in this representation we will add an CLS token in front of this vector. So this you can think of a vector, and separator token will be added at the end of the vector, just to separate the sentences. So this CLS token would be empty in the beginning, but when the whole process like tokenization through context vector generation, the CLS will have the richer representation of this entire sentence, holding the deeper meaning between these words present in the sentence. So yeah, so step number one, tokenization is done. They are converted into numbers, unique numbers, and CLS and separator tokens are added. Okay, so this is to just to help you visualize how the process is going on. So I'm sorry, this is hidden. So best selling music artist. So this is how the tokens will be. So you see this hyphen is also considered as a token. And the next step, we will create an embedding. So now these tokens are converted into a unique ID. So this best will also have its unique ID, and along with that, this best will have a set of embeddings. So this we call it as a non-contextual embedding. That is, these non-contextual embeddings are coming from the training data set from which these enterprises are building these large language models. So maybe this minus 0.11 can actually denote the word smile, so which should have occurred more frequently with this word best in the training corpus. These training corpus can be Wikipedia articles or vlogs, blogs, social media handles. So whatever those enterprises have chosen, so from that these vectors are built. Why we call this as a non-contextual embedding is that, so this vector, the embedding vector representing the best, is only talking about the best in the training document, but it has not so far captured how this best is going to relate with the rest of the words in the sentence. So that is context vector. So if you look at here, so our ultimate goal is to build a context vector generation, but as of now, we are only building a non-contextual embedding. So it comes from the training data set. Yeah. Okay. So why the beauty of these embeddings is that, like, you can do numerical operations on these embeddings. You can do addition and you can do subtraction. And while we do so, they also capture the semantic relationship inside it. So for instance, if we take the king embedding, so when we look at king, we can create an embedding from the training document wherever the king is, the word king is associated with the words frequently. So those will get to form the king embedding. And we take the women embedding the similar way. You add it and you subtract the man embedding. So the resultant embedding will be actually representing the queen embedding. This is actually true, and you can cross-check the code. You can get it from ChatGPT or any web resources, and you can check that it is true. Okay, so now we have already seen the step number 3. So we constructed the embeddings for the token, each and every token. So the dimensions will again vary from one large language model to the other. So for instance, this 768 is the length of the embedding for a single token, is for the BERT large language model. So this is the fixed size for each and every large language model. So finally, you will get a number representation for the each and every word. You will get a embedding like this. Then we have something called positional embedding, because a text is a sequential structure. So when we change the positions of the structure, the entire meaning changes. So these large language models are taking care of these positional embeddings also. You will understand this better when you look at this. So let's say this is the dog. We give the dog, and this is the dog embedding. So you see this, a dog is closer to horse and cat. That means like they are semantically closer. So these words will actually be in the embedding of the dog. That's what it means. Let's say like AJ's dog is a cutie. So this is the first sentence. Here you take the second sentence. AJ looks like a dog. The position of the dog changes, the meaning changes, because in the first sentence it means the dog, and the second sentence it actually means the AJ himself. So yeah. So what I mean to say here is that, like, the position changes, position of a particular word changes, the entire embedding of that word that can carry would change. So here this dog embedding would have horse and cat, but this dog embedding will actually carry information about AJ. So that's what is the core idea. So here we are adding the embedding of dog with the positional embedding of the dog to just capture. So what is our goal? We are deeply understanding the sentences. So that's what is our goal. And as in that step, like in that journey, we are adding the positional embedding. Okay. So after we are done with the positional embedding, so now we have to do the multi-head self-attention and feed-forward network. So before understanding this slide, so we must understand what is a self-attention before we understand multi-head self-attention. So we'll understand that first. The self-attention mechanism, as we talked earlier, like so many times we have seen in this part 1 and part 2, like it is the mechanism through which the large language model is able to capture the relationship between the words. But how it is done? It is done by using these three vectors: query vector, key vector, and value vector. So this is the attention. This is how the attention score that is calculated between a query vector and a key vector. So we take the dot product of the query vector and the transpose of the key vector divided by the dimension of this each word. So you will understand this better when you look at this picture. Yeah. So this is this is how the attention works. Like this is the sentence given: a nice walk by the river bank. So these are the non-contextual embedding that we created in the step 2. In attention mechanism, what we are trying to do is that we take this word and that is the query word, and the rest of them are keyword. We take this embedding vector and try to build a dot product with with nice, with walk, with by, and the rest of them. So when we do this, and we also take the word nice and do a dot product with the rest of the words. So when we do so, the two vectors we will understand, two vectors will have most similarity, and those two words will actually have the importance in that particular sentence. So now you can think of the scenario like when we give a prompt, like why ChatGPT is giving attention to only certain words. So that's why the word attention is given here. So the math behind this is dot product. So the attention is nothing but like it is understanding what are the words that are important for me to interpret this entire sentence. That's the way we have to think about it. To understand the query and the keyword vector, so we can look at this picture so we will understand. So the query token, so initially this is the query token. We are understanding how this word on is important when it is, how this word on is related to the other words. So this is the query token as of now, and the rest of the words are the key token. So this is the sentence, and the rest becomes the key token. When we do the dot product of on with the, river, bank, and they, and I'll talk about the mask now. So once we are all done with this, and then we will shift the query token to the, and the rest of the tokens becomes the key tokens, and this process is repeated until we complete for all the sentence. So now we will understand what is this mask. So as I said, all these processes are happening when these enterprises are building the large language models. So these are self-supervised models. So they when they train themselves, so when they are done with the one iteration of interpreting all the sentences in the training document, and they try to test themselves, like how powerful they have become. To do that, they mask 50% of the words, and they try to predict the rest of the 50%. They test themselves, and if they are doing it correctly, so then the weight adjustments is done accordingly in the next iteration. If there's so many words that are predicted wrongly, they back propagate, they adjust the weights, and then they get better, repeat once again. So this process is repeated again and again until they get they feel that they are able to predict most of the words given in the training corpus. So that's how they are building themselves as the next word predictor in this training phase, like in this journey. So that's why we have this mask here. Yeah. So that is what we see. So now you should be able to understand this slide. So the attention is taken by the, attention score is calculated between a query vector and a key vector. So we have a query vector, the word on, and the rest are the key tokens, and we take they're all going to be in the matrix. You will understand when we take an example and work out. So then take a dot product divided by the square root of the dimension. What is this dimension? Dimension is nothing but the each token vector size. So we saw here that the dimension of the each token embedding is 768. So that is what we mean here. So we are just dividing it because the square root of 768, like if the large language model is but like why, because like these deep learning architectures don't like larger numbers. So they want to actually minimize the numbers. So we are trying to squeeze the numbers, and so that's why we're doing this math. Okay, so and then normalize scores using softmax. So we take a softmax of the score because softmax function squeezes the score to lie between in the range 0 and 1. So again, so these models want to have a minimalistic number, so it is easily tractable that way. Okay, so we said like query and key we have finished, but we have not talked about value. This value vectors, the value vectors is multiplied again with this softmax softmax scores to get the final attention. So the value is again nothing but so the entire this value vector is nothing but initially the embedding will have some values, and how the weights how finally at the end of the training phase, like these weights are updated, so those will be in the value. So when we multiply all together, so we get an output. So this eventually this score given for each and every word in the matrix will tell us like how much information that particular word has captured the relationship between the other words in the given sentence. So that's self-attention. So having understood this, like now it is rational to understand. It should be easy to understand the multi-head self-attention. So multi-head self-attention, even before looking at here, I'm sorry, I'm traveling back and forth. So we need to understand, if we look at this, we will understand it better. So this is a self-attention mechanism. So out of self-attention mechanism, you will get one output, right? So we had query, key, and value. You get Y31. Like you do this process n number of times, that is multi-heads. So then you get, so here we have 3 heads. So you get output from 3 output. So 3 heads. So you just squeeze them together as a single output using the feed-forward network. So now we will understand that the components of the encoder architecture. So here is where we saw self-attention and feed-forward. So this feed-forward mechanism is just to squeeze the output into a single representation. So that's what. So that is about multi-head self-attention. Even better, so if you look at this, you will understand. So this is self-attention visualization. So we had input embedding. This is the non-contextual embedding we created. We had query vector. We had keys. We did a softmax, and we got a non-contextualized embeddings as the final output, right? So this is this self-attention. So this is done multiple times. So that's how you visualize multi-head. So multiple times this entire thing is repeating itself. So what these each time heads do? So each of the time, each word is focused on multiple dimensions of the word. For instance, if we are building, we are talking about the word apple, each and every time the word apple, so the apple fruit or Mac apple, so sometimes the grammatical category, there should be a multiple dimension for a particular word. So each and every time the entire process is repeated in multiple dimension by these large language models to understand the sentences in a deeper way. So now you will get to know like now how these models are trying to mimic the way the humans are understanding the language. Now it should be easy for understanding the multi-head self-attention. So once we are done with the self-attention, we have multi-head self-attention, and we squeeze them to get a single representation. Yeah. So that's about it. And finally, we will concatenate all the heads and we give it to the feed-forward network. This will give the single representation of the input sentence. So now we are ready with the context vector generation. So we had an very naive token representation, and then we created non-contextual representation. So tokenization we had, and we had a non-contextual embedding plus the positional embedding, and through the multi-head self-attention mechanism, we got the contextual vector generation. So when we in the upcoming slide, we will understand through an example how these numbers play around to capture the relationship. Okay, so that is about the context vector generation. So once we have this context vector generation in our hand, so we are now free to build any application on top of that. All these vector is placed in the CLS token that we saw earlier. And now we can use this vector either to build a translation or to do a predictive task and whatnot. Yeah. So that's the story of the transformer. As I promised earlier, now you should be able to understand the each and every components of this transformer architecture published in the Google paper. So this is the encoder and this is the decoder. So we'll see from here. So the input sentence is given, input embedding, non-contextual embedding, positional embedding, multi-heads attention, and then feed forward. And this output is given for the decoder to interpretation. So decoder also does the same. So masked multi-head attention. Then we have the output probabilities. So why we have the softmax and output probabilities? Like even when we spit an output by the large language model, it will always throw an output probability. How much probability that this translation or that this prediction is true. So that's how we will see. So the output will be in the natural language sentence, obviously, but the probabilities indicate like how much probability that output is true. So hope you understood the components of the architecture. So we'll now see with an example how these math work. So we've already seen like how the mechanism work. We will take an example with numericals and we will understand what's happening inside. So as we saw, the scores is between the query vector and the transpose of the key vector. So attention weights is between the softmax. We take the softmax of this and the output is the attention weights multiplied by the value vector. So that we know. So we'll take an example. So these are the, we have to visualize them as a matrix. So query matrix, key matrix and a value matrix. So what is a query matrix? It is X is nothing but the input embedding that we had earlier, right? Like after the step number 1 and 2, we had a non-contextual embedding. So that is X, and we will have a weight matrix. So the same dimension of this input matrix. So the weight matrix will have a random values, like it can be 0 even. So like it will have a random value initially. This weight matrix is very important. Like so this is going to finally get better and better during the training process, and it will have the appropriate weight at the end of the training process. Similarly, key matrix. We have a different key matrix for the key vectors. X is again the input and value also the same. So we have a weight matrix for the value. So all these WQ, WK and WV are random weights initialized before the training phase. So we will understand how these get better. So we'll take an example. The cat eats fish. So we are going to see like how these vectors are created for this sentence. So the input embeddings will have the first row will have the embedding of the, and the second row will have the embedding of cat eats in the fourth row, and the fifth row the fish will be there. Okay. So now after let's assume that like this WQ was a random value, so it will also be looking similar to this Q matrix, but we have multiplied that weight with this X, and we got this matrix. So you assume that this X matrix and WQ is multiplied, and this is how we've got the query matrix and key matrix and the value matrix. So when you look at this query, the query encodes what a word is looking for. So I hope we still remember what was the query token. The query is under it's looking for like what are the words that is important to a particular word. So that's what the key represents, how relevant each word is for the attention. And finally, the value will actually have the actual information finally multiplied with these two, like it will pass on the values to the next layer for the further processing. So that's how we understand. Okay, so attention scores. So like we had a query and key. So we get the attention scores by multiplying query vector and taking a transpose of the key vector. So now if you look at this in the third row, so what is third row? So third row is representing the eats, right? So the third row represent eats. After attention weights, the query and key. So I have been taken a dot product, and that's what it means. So this the third row is this vector, means that mostly influence on itself. So what this word means, this is eats itself and also attends to the cat. So the first word is the eat, and the rest, this is the query token, right? And the rest of the words are the key tokens. So this point to, this point to is the cat. So it is, it is next to itself. So when it is given attention, so the word eats is very much important to itself only, and the next to it, and it is most important to the cat. It is point to, and it is not relevant to the word the. So it is having a lower value. So that's how it is. It should be understood. So the first row represents the embedding of the word the, right? Like we will understand. So the is having, so if you look at this, the cat and eats. So these are the word representing the cat and eats. So these are having the higher numbers. That means the word the is very much attached to the word cat and eats. That's how we should understand. Okay, so now we got the word output as eats. So zero point 0.5, and so we got this from this vector 0.5. So we take this vector and multiply by the value vector from where this value vector came. So here, from here we got the value vector, and this is the final. I'm sorry. So this is the value vector. So we are taking a multiplication, and finally we get the richer context representation. So the richer context representation, if you look at this, it's a 3 dimension, because like the input length is 3 dimension is fixed here, like it is not 768. So for easy understanding, so we fixed it to be 3 dimension. So now this eats is represented as a representation of this 0.64, 0.54, 0.39. But these numbers inherently capture how much it is coupled with the words cat and fish. That's what these semantic information is encoded in this vector. So that's how it should be understood as. So this value vector is like, as we saw earlier, like this value vector will encode the information of each and every word, like how much they are related with the other words, and they are encoded there. So if you look at it, the final takeaway is that, like if you look at the initial representation, this is the non-contextual embedding obtained from the step 2. And after training, we get this context aware embedding. So finally, how we should understand all this is that the initial representation, is not context aware, but the final embedding will be context aware. But when you look at the word the most of the numbers are not changed. Why? Because like the itself is not very much attached to the context, so it is not very much important. So, but whenever when you look at the word cat, it has actually changed. That means like it is trying to capture the relationship between the other words. So when you take eats, so eat is the verb of the sentence. Like the verb is very important for a particular sentence. So it will be mostly attached with the subject and the object. So that's why you see the higher numbers for cat and fish captured in the number representation. So likewise, like the for fish is also like changed, but the for fish the most higher number is like eats. So why? Because like it is more attached with the verb. So what I'm trying to, so finally how we should understand all this is that like the context representation is the context representation of a particular sentence is based on how each and every word are semantically coupled with the other words. So that's what is done here. So this is done by capturing the dot product of the weight vectors, and these weights are like not happening in one iteration. This is happening in multiple iteration. So this is what I had to say, like to about how to understand like what's happening inside the transformer. So I hope you understood the math behind the transformers. Thank you so much.